Okay, so I'm going to start going over homework number 7. Feel free to let me know if you have any questions, or if there's another worksheet that you have questions about. Feel free to ask that. All right, so here's number 1. Function g has a derivative g prime, where g prime is decreasing and twice differentiable. Selected values of g prime are given. What can we conclude using mean value theorem on the interval from 1 to 10? Okay, so we can basically apply mean value theorem using our table of values here. So here are our endpoints. So we can make the conclusion that we can guarantee a slope off of the second derivative graph, or the value of the second derivative graph, basically a slope coming from the first derivative graph. So A and B are 1 and 10. So whatever the slope is between the endpoints of my G prime graph, there must be an exact steepness somewhere along the curve as well. So we go to our table. G prime of 10 is G prime of 10 is 0. G prime of 1 is 9. So we can guarantee that there must be a second derivative value of -1, or in other words, there must be a slope of -1 somewhere along the curve. Okay. Part B, use left Riemann sum with 3 subintervals. From 1 to 10. So we're looking at the area under the G prime graph. So we find all the widths, 2, 1, and 6. Width times height for each of the rectangles. Let's see, we're told that our G prime graph is always decreasing. And we're dealing with the left Riemann sum. So let's just sketch something out to convince ourselves whether we're looking at an over or under approximation. So there's my decreasing graph. I'm going to attach the left endpoint of each rectangle, left upper corner to the graph, and I should be able to convince myself, okay, I'm dealing with an over approximation. Okay, any questions there?
Mr. Yang?
Yes.
Can you just explain how you got the over approximation part again? I'm sorry.
Right. So we have two things that's giving us the information. It says that the function g has derivative where g prime is always decreasing. And if a function is decreasing and you're creating left Riemann sums, attaching left endpoint of every upper left corner to the graph, you're going to get these rectangles that are all peaking above the curve. So we know the area of these rectangles are going to be actually higher than the will be higher than the actual area under the curve. So yeah, since G prime is strictly decreasing on the interval from 1 to 10, then a left Riemann sum will over approximate the actual area.
Okay, thank you.
Mm-hmm. Okay, everybody good? Okay. Part C, similar to what we did in class, going through use substitution. Okay. So we start off with that portion inside. We'll push that -3 out as -1/3. We know through the integral process that G double prime is going to convert into G prime of U, and then we can worry about how to work in those bounds.
Why is -3 the upper bound?
That's just the way the problem sets up. I wouldn't say that we do. You can and push a negative outside, but I would say that you definitely want to change those bounds if you're trying to read the graph. If you're trying to read from left to right and it's telling you to go from right to left, then I would worry about the bounds being out of order. But if you just evaluate it the way it is, it'll still come out to be the right answer. So for me, I don't go through the trouble of changing the bounds unless I'm trying to pull information from a graph. Okay, any questions from here to here? This is the calculus. We're done. We're basically done with the calculus. Now we're just trying to get in our trying to work in our bounds here. So we could convert these x value bounds in terms of u, but I think it's a little faster if we just get everything back in terms of x. So I'm going to take this antiderivative and just going to get this back in terms of x, and then I can rely on the bounds. Okay, upper bound first. If I insert -3 in for x, I get 1 + 9, which is 10. Minus, then repeat the process for the lower bound. 10 + 3 is 4. Okay, we have specific values from our table that we can insert in. G prime of 10 is 0. G prime of 4 is 5. And that's just going to give us 5/3. Okay, any questions? First page. Parts D and E, these are more like carryovers from the previous FRQ. I'm not going to put this on the test, but this is L'Hopital's rule, and E is product and chain rule. Okay. So it's good practice, but it won't be on the test tomorrow. Let's go to F, and if we have time, we'll go back to D and E. So this is a solving differential equation here.
You said D and E will not be.
Right, won't be on the test. But you recognize this, right? This is just L'Hopital's rule.
This is a more complicated version.
Well, yeah, but you saw this on the previous test, our previous quiz, right? You just have to find it, plug one in, you'll get 0 over 0. Then you have to do e to the u times u prime, find the derivatives, bunch of chain rule going on, and then you reevaluate, and you get down to the answer here. Yeah, it's a bunch of L'Hopitals here, and then part E is just product and chain. And then once you get everything spelled out, then replace all the x's with 2 and use the table to get it down to a number. Yeah, but we'll go to F. Okay, so we're going to set up. I'm only given y prime, so we're going to rewrite this as dy dx. Get my fractions going. Cross multiply. Once I cross multiply, I see dy is nicely sitting in its right spot. Dx is also sitting in the right spot. We just have to make sure the rest of the terms are in their right places. We do have one thing out of place, that what is 1 minus 2y is going to be, and we're going to divide that over, make it go in the denominator of the left side. And now we have full separation. Okay, take the integral. Use substitution on the left, and then first theorem on the right. Okay. A little bit of cleanup. Natural log on the left, integral g double prime on the right. Replace the u back in terms of x, or sorry, in terms of y. Okay, so I have my general equation. We can either solve for y first, or we can solve for c first. Yeah, I think there's enough messiness here. Maybe it's just faster just to get that c value right here. So I'm going to go ahead and replace 1 in for x, 0 in for y, and try to get that c value resolved, and I can work towards getting that y by itself. g prime of 1, we go to our table. It's going to be equal to 9. Natural log of 1 is just going to be 0. Okay, we go back to where we started making that substitution, and then we can try to get this mess to clean out to be just be for y. So now my goal is to get that y by itself. So I have a couple of things I have to resolve. I'm gonna have to move this -1/2 over to the right side. Got to resolve the natural log, and then finally I got to get down to just to be y by itself. Yeah, multiply by -2. Now, E is the base. Drop the absolute value. Plus or minus will show up. Subtract 1, divide by -2. Okay, this is a little messy here. I'm still leaving that plus or minus because I just want to make sure that I have the right answer. So the way I'm going to double check it is I'm going to insert 1 back into the equation, and I should get a 0 back in return. So I'm going to test the positive version first. Normally I would, yeah, and also this y value is not as helpful as before because it's not positive or negative values. So I think there are times when we just have to, just double check it and make sure that we are using the right form. Okay, so here's the positive version. If I enter 1 in, let me see if I get 0. So if I enter 1 in for x, I get g prime of 1, which is 9. 9 times -2 is -18. Negative 18 plus 18 is 0. E to the 0 is 1. I'm left with 1/2 plus 1/2 is not equal to 0. So I'm going to have to make an adjustment. Looks like I need that negative here to fully confirm that this order pair is truly going to make it work. So normally we don't have to go through this process of doing that additional check. If you're dealing with square roots is going to be very clean. Like whatever that y value is, it's going to be the sign. But if you're not dealing with square roots, sometimes it's safest to just double check it. Whatever answer you get, go ahead and try it with the order pair and see if it actually works, right? If it doesn't work, then that's an indication that you probably need to switch the sign. So I would switch the sign, double check it again, and that just give you some additional peace of mind that your equation is not only right, but then you also are picking the correct plus or minus to match what's needed for the equation. It says then use the expression to find k of 3. So technically we should be plugging 3 back in here, but I won't ask you to do that on the test. Just going to ask you for the general equation.
I have 2 questions. One, can you show us what a subfield problem is?
Yeah, off of homework number 5. Homework number 5 was from last Thursday. Oh, that's a whole class. Yeah. This is number 2. This is from Thursday. Yeah, we can do this one here. Consider a differential equation, dy dx equals y squared over x minus 1 on the axis provided. Sketch a slope field. So take each of my order pairs. Plug 0 in for x and for y. If I plug 0 in for x and y, I get 0 over 0 minus 1, which is 0. So that's just going to be a slope 0 there. Here's the horizontal line. Next up, 0, 1. Plug 0 in for x, 1 in for y, so 1 over that's negative 1. So I'm going to fill this order pair in with negative 1. Next up, 0, 2. 2, 0 in for x, 2 in for y. I get 4 over -1. So I'm going to make this an even steeper slope. Okay, 2, 0. 2 in for x, 0 in for y. Horizontal line. 2, 1. 2 in for x, 1 in for y. And then 2, 2. And if you get undefined, then you leave it empty. For instance, let's say there were dots here along. Let's say there's dots at 1, 0, 1, 1, and 2, 1. If you enter them in here, you're going to get a value over 0, which is undefined. So if there were dots here, you would leave those empty. Okay, let's finish this B and C here. Just more linear approximation and solving differential equations. So B is linear approximation, where we're just going to gather information about order pair, point slope form, and then we can use that to do linear to use that tangent line to approximate a value on the graph. Okay, so order pair 2, 3. We need a slope formula. We need a slope. Slope comes from the differential equation. Okay, so insert 2 in for x, 3 in for y. Once we have our y by itself, we can use that to approximate f of 2.1. Okay, solving differential equation for part C. Okay, first things first, let's cross multiply, see where that gets us. So if we look, dy, dx are locked in, those are good to go. But we see the x minus 1 and the y squared being out of place, right? So they're both going to have to divide over to the other side. They're going to both end up being in the denominator on the other side. So we got to divide the y squared over, and we got to divide the x minus 1 over because they're not in the right places. Okay, how does that look to you? Good, okay. Okay. Separation of variables. Now we can move to our calculus portion. Left side is power rule, right side is natural log, but this y squared is out of place. Okay. Power rule on the left side. Oh, the right side is a little bit of u substitution, but you can also just recognize this as a natural log, but we can go through that process. So we add 1 to the exponent. This ends up being just natural log of u, or natural log of okay. Good on the left and the right side. All right, we still have quite a bit of cleanup ahead, but at least we're done with the calculus portion. You guys okay? Okay. Let's see. I'm going to go ahead and solve for C here, but maybe do a little bit of cleanup if I can. Okay, so I'll fill in my order pair 2, 3. Natural log of 1 is 0. C is just negative 1/3. Okay, I'm going to multiply everything through by negative 1. Just to get that left side to be just positive. Okay, I want to flip that y, but if I flip the y, I got to flip this entire expression as well. So it's not going to look very pretty, but I'm just kind of flip-flopping everything here. So left side, I'm going to flip-flop it to be 1/1, and the right side, I'm going to flip-flop it. It looks messy. We're dealing with a complex fraction, but as long as you get y by itself, it doesn't really matter how ugly that right side looks. Okay, any other questions? Okay, so tonight, if you guys can go through worksheet 3, but also look to the previous work that we did. You can start all the way at homework 1 if you like, but you can skip area volume, you can skip antiderivative word problems, but I think everything else is going to be good for you to look through.
Can we go over a particle motion?
Mm-hmm. Okay, there's a question about particle motion here, so I can pull the day 1 material here. This is from last Monday. Okay, I'm just gonna pull the key up here. This is from last Monday. Okay. Particle motion, Riemann sums, notes day 1. This is from Monday 4/12, I believe. Yeah, Monday 4/12. Okay, so it says a car travels on a straight track. During that time interval from 0 to 60 seconds, the car's velocity, measured in feet per second, and acceleration are continuous functions. Using the appropriate units, explain the meaning of the definite integral from 30 to 60 of the absolute value of v of t. So we know what this means because we've talked about it, going through some of the formulas there. That's just the formula for total distance. If I accumulate all the velocities under the graph, I'm basically converting all of these areas to be positive, and that will give me total distance. Because if I move 5 units left, 3 units right, 1 unit to the left, it's still a total movement of 9 units. So the absolute value just ensures that we treat every movement as a positive value. So We know the integral of v of t, absolute value of v of t, is the total distance traveled between 30 and 60 seconds. And then it says use trapezoid approximation. So trapezoid approximation is formula is 1/2 width
Oh, wait, okay.
Yeah, so we pull from a table. We can find the width by subtracting all the sub intervals from t. But we got to be careful here. It's the absolute value of v of t, so we have to, if we see any negatives, we got to treat those as positive velocities. So 1/2 width times height 1 plus height 2, and then we repeat the process for each subinterval. It takes us all the way down to 185 feet.
See, okay.
Mm-hmm. Okay, part B. Using appropriate units, explain the meaning of the depth integral from 0 to 30 of a of t. So we can go through a little bit of yeah, we can go through first theorem, right? We can push that integral up to v of t, and then we can say the integral of v of t, sorry, integral of a of t is just v of b minus v of a. So that means the integral of a of t of from 0 to 30, it's just going to be v of 30 minus v of 0. And if we look at what those values mean, this is velocity at 30 seconds, that's velocity at 0 seconds. So all this is telling us is telling us that if we're subtracting the velocities between those 30-second period, that means it's giving us the change in velocity between those two time periods. So we're traveling at -14, then we're traveling at -20. What's the difference between those two values? That's a difference of 6 feet per second.
What's the difference between IVT and MVT?
Right. So MVT is where you are guaranteeing a slope of the graph. IVT is you're guaranteeing a point on the graph based off that exact value. So, for instance, if you look at part C, can we guarantee a place where velocity is -5? Well, if you look at your velocity numbers, it looks like we can, right? Because all this is continuous. We can't go from -10 to 0 without crossing -5. So if you're just reading a table and you're realizing that, wait, I don't see the number in front of me, but I see a number below and I see a number above, so I'm just going to conclude that it's got to at least cross through at some point. So if I'm just relying on a table of values without having to look at the derivative or integral, then I can rely on IVT. So I can say that -5 falls safely between -10 and 0. I know it's a continuous function, or my velocity is going to travel between those two numbers, so it's going to have to cross through -5. But for D, we have a little bit more involvement. Because if you look at D, it says, is there a time when acceleration is 0? And if you look at acceleration, we're not going to be able to make that conclusion, right? Because it doesn't look like our acceleration is going to hit 0. But does it mean that it's not going to hit 0? Because we have all this missing information, right? Maybe it dips to 0, but we don't even know it. But maybe velocity can help us out, right? Maybe velocity can help us out, because if you look, this means when it says, is there a time when acceleration is equal to 0? Another way of thinking about this is there a time when the slope of the velocity is equal to 0? So if I think about it that way, then what if I just graph these points here? You see how there's a repeat value, -20 and -20? So if I were to graph my velocity function, let's say I graph 0, -20, and then I graph 15, -30, and then I went back to 25, -20, my graph is basically going down and coming back up. In that process, it has to hit slope 0 because it's telling us it's continuous for both functions, so it's basically differentiable for v of t. So here, just by graphing a bunch of these values from velocity, I can convince myself, okay, I see a slope 0. It may not occur here, but it's going to have to occur somewhere because it's going to go down to -30 and come back up. Maybe it dips a little bit lower, but there's got to be a slope 0. And because of that, we can rely on Rolle's theorem to conclude that there must be a slope 0, which means there must be acceleration 0, even though acceleration 0 is not showing up here. And then here's a picture to convince you of that. All right, hopefully that helps. And then, yeah, encourage you guys to go through the rest of the worksheets, go do the morning review beforehand. So tomorrow, if you come to the morning review, you can just follow along, and or if you have any questions, you can you'll be able to have a very specific question to ask to help you further your understanding rather than looking at it for the first time tomorrow, if possible. But. All right, thanks guys. See you tomorrow.